Welcome to our deep dive into algorithms. We'll be going through the book Grokking Algorithms to see what makes these so interesting. Algorithms might seem like just something that computer scientists deal with, but they're actually everywhere. They power everything from online searches to GPS.
Right. At their core, algorithms are simply sets of instructions. Think of it like a recipe, like for baking a cake.
Okay, that makes sense. So let's jump into one of the first algorithms the book tackles, binary search. Sounds technical, but I bet it's something we use all the time without realizing it.
But absolutely. Imagine you're looking for a word in the dictionary. You're not going to flip through every single page, are you? You'd probably open it up somewhere in the middle and then decide to go forward or backward. That's essentially binary search. It keeps having the problem space until it finds what it's looking for.
So it's not checking every single possibility, it's eliminating a big chunk of options with each step. That's pretty clever.
Exactly. That's why it's so much faster, especially when you're dealing with huge amounts of data. Think about searching for a specific website among millions on the internet. Binary search helps search engines find what you need like that.
Wow, I never thought about it that way. So how do we measure uh, just how efficient an algorithm is? The book mentions something called Big O notation. That sounds kind of intimidating.
It's not as complex as it sounds. Big O notation basically tells us how much longer an algorithm takes as the problem size grows. So it's not about measuring time in seconds. It's about how the time increases as the problem gets bigger.
Oh, okay, that makes more sense. So binary search is really efficient because its time doesn't increase drastically, even if the data set gets much bigger.
Exactly. Binary search has what we call logarithmic time complexity, meaning it can handle huge data sets without a problem. Remember the example of landing a rocket on the moon?
Yeah.
NASA uses binary search. When speed is critical and the data is vast, it just works.
Okay, so that's amazing. So we've talked about binary search. What's next on our algorithm adventure?
Well, let's talk about data structures. Those are the building blocks of a lot of algorithms. Two fundamental ones are arrays and linked lists.
All right, let's break those down. I remember these being a little confusing when I first learned about them.
Think about it like organizing your music collection. An array is like having all your CDs on a shelf. Easy to access any CD you want, but what if you want to add or remove CDs from the middle?
Yeah, that would be a pain. You'd have to move everything.
Right, exactly. And that's where linked lists come in. It's like if each CD case had a little note inside telling you where the next CD in your collection is located. That's essentially a linked list.
So you can just insert another CD anywhere.
Right. You can easily add or remove CDs anywhere in the chain, but finding a specific CD might require you to follow the chain from the beginning.
So arrays are great when you need to access things quickly, and linked lists are better when you need to add or remove things easily.
Exactly. And even though these seem simple, they actually underpin way more complex data structures used by companies like Facebook to manage tons of user data.
Okay, that's pretty mind-blowing. So these seemingly basic ideas are actually driving some of the technology we use today. What's next on our algorithm exploration?
Let's tackle something that often trips people up. Recursion.
Hmm.
Don't let the name scare you. It's a really powerful technique once you wrap your head around it.
Recursion. Yeah, I vaguely remember it, but I'll admit it always seemed a bit mysterious.
Think about those Russian nesting dolls. Each doll contains a smaller version of itself. That's kind of what recursion is like. It's a function that calls itself to solve smaller and smaller pieces of a problem.
Okay, I'm intrigued. Can you give me a more concrete example?
Sure. Imagine you're searching for a file on your computer. You start with a folder. If the file isn't there, you check all the subfolders. And if those subfolders contain more subfolders, you check those too. That repetitive process is a lot like recursion.
So it's basically repeating the same action until it finds what it's looking for.
Yes. And recursion needs something called a base case to tell it when to stop. Otherwise, it would just keep calling itself forever.
Oh, that makes sense. Otherwise, it'd be like an infinite loop.
Exactly. And when used correctly, it can be a really elegant and efficient way to solve problems.
This is all so fascinating. Algorithms really are like these hidden engines driving so much of our world.
They truly are. And we've only just scratched the surface.
Well, I'm ready to keep going on this algorithm adventure. What's next?
Ready to conquer another algorithm. Let's talk about divide and conquer. It's a clever problem-solving technique.
Divide and conquer. I like the sound of that. It sounds very strategic.
It is. Imagine you have a giant jigsaw puzzle. Instead of trying to put it together all at once, you divide it into smaller sections. Solve each section and then combine the solutions. That's divide and conquer.
So it's about breaking down a big problem into smaller, more manageable pieces.
Exactly. And one of the most famous examples of this technique is the quicksort algorithm. It's used to sort lists of items very efficiently.
Quicksort. Yeah, I've heard of that, but I've never really understood how it works.
It's actually pretty simple. Quicksort picks a pivot element from the list and then divides the rest of the list into two parts, elements smaller than the pivot and elements larger than the pivot. Then it recursively sorts those smaller parts until the whole list is sorted.
So it's like a recursive sorting dance. It keeps dividing and conquering till everything is in its right place.
Precisely. And because it breaks down the problem, quicksort is much faster than simpler sorting algorithms, especially when you have a lot of items to sort.
Okay, that makes a lot of sense. So what other algorithms use this technique?
Well, another sorting algorithm, merge sort, uses a similar approach. It divides the list in half, sorts each half, and then merges the sorted halves together.
Oh, so it's like a recursive merging symphony. It's amazing how these algorithms break down complex tasks into such elegant steps.
Right. And the beauty of divide and conquer is that it's not just for sorting. It can be applied to a lot of different tasks.
This is all so fascinating. I'm starting to see algorithms everywhere now.
That's the fun part. Once you start recognizing them, you'll be amazed how much they impact our lives.
Okay, I'm ready for our next algorithm adventure. What else do we have in store?
Let's delve into the world of hash tables. They're like the superheroes of data storage and retrieval, known for their speed.
Hash tables. I've heard of them, but I'm not sure I fully grasp what they are. They sound pretty powerful, though.
Okay, think of it like a well-organized library. Instead of searching through every single book to find the one you need, you have a card catalog that tells you exactly where to find it.
So it's like a super efficient indexing system.
Exactly. It uses a special function, called a hash function, to convert keys, like a book's title, into specific locations in a storage array. This allows us to find information in constant time. That's incredibly fast, even faster than binary search.
Wow, that's impressive. So no matter how much data you have in a hash table, you can find what you need almost instantly.
Pretty much. Of course, there can be issues like collisions, which happen when two different keys map to the same location. But there are ways to handle that, like using linked lists.
So even when there are bumps in the road, there are ways to keep those lookups speedy.
Absolutely. And that's why hash tables are used in so many real-world applications. They're behind everything from preventing duplicate entries in voting systems to caching data in web servers.
Okay, that's amazing. Hash tables are like the unsung heroes of the digital world. I'm
Yeah.
definitely starting to appreciate their power.
And we're just getting started. There's so much more to explore.
Well, lead the way. I'm ready for our next algorithmic discovery.
Let's dive into the world of graphs.
Hmm.
They're not just for math class. They're incredibly useful for representing relationships and connections.
Graphs. Okay, I'm intrigued. I know graphs can show relationships between things, but how does that translate to algorithms?
Think about a social network, like Facebook. Each person is a node, and each friendship connection is an edge. A graph can represent this entire network, showing how everyone is connected.
Okay, I can see that. But what kind of problems can we solve using graphs and algorithms?
All sorts. Imagine you need to find the shortest route from your house to a friend's house. Or maybe you want to connect all the computers in a network using the least amount of cable. These are all problems that graph algorithms can solve.
So graphs help us navigate complex networks and find solutions.
Exactly. And there are lots of different graph algorithms, each with their strengths and weaknesses. One of the most fundamental ones is called breadth-first search.
Breadth-first search, what does that do?
Imagine you're searching for someone in a crowded room. You might start by asking the people closest to you if they've seen that person. And if they haven't, they might ask the people closest to them, and so on and so on. That's essentially how breadth-first search works. It systematically explores a graph, level by level, until it finds what it's looking for.
Oh, so it's like a ripple effect, spreading outward from a starting point until it finds the target.
Precisely.
Yeah.
And because it explores the graph layer by layer, breadth-first search is guaranteed to find the shortest path between two nodes.
Okay, that makes sense. So it's like finding the most efficient route on a map, but instead of roads, we have connections in a network.
Exactly. And breadth-first search is used in a lot of real-world applications, GPS navigation systems, to find the fastest road.
Wow, that's amazing. I'm starting to see how these graph algorithms are like superpowers, helping us find our way through complex networks.
They truly are. And there's so much more to explore within the realm of graphs.
Well, I am eager to continue our journey. What other graph algorithms are waiting to be discovered?
Let's step it up a notch and talk about Dijkstra's algorithm. It's a more sophisticated approach for finding the shortest path. It can handle situations where the edges of the graph have different weights, representing things like distances, travel times, or costs.
Okay, so it's like breadth first search, but with some added complexity.
Exactly. Think about finding the fastest route from your house to work. Some roads might be faster than others because of traffic or speed limits. Dijkstra's algorithm takes these factors into account and finds the shortest path, even when the weights aren't equal.
So it's like a super smart GPS that considers all the variables to find the most efficient route.
Precisely. It keeps track of what are called the cheapest nodes, those with the shortest known travel time, and updates the costs of their neighbors as it explores the graph, ensuring it finds the optimal path.
That's incredible. Dijkstra's algorithm sounds like a real game changer for navigating complex networks.
It is, and it's used in a wide range of applications, from network routing protocols to logistics.
Okay, I'm definitely starting to see how these graph algorithms are essential for solving real-world problems.
And we're just scratching the surface of their capabilities.
Well, I'm ready to dive deeper into this world. What else is on our agenda for this deep dive?
Let's explore a different approach to problem solving: greedy algorithms. They're known for their simplicity and speed, although they might not always find the absolute best solution.
Greedy algorithms, that sounds intriguing.
They can be a bit like that. Imagine you're trying to pack a suitcase for a trip. A greedy algorithm might say, just grab the biggest items first, then the next biggest, and so on, until the suitcase is full.
Okay, that's a simple approach, but wouldn't it potentially leave out some smaller items that could have fit?
Exactly. That's the trade-off with greedy algorithms. They're easy to understand and implement, but they might not always lead to the optimal solution.
So it's like making decisions based on what seems best at the moment without necessarily considering the long-term consequences.
Exactly. And while that might not always be the best strategy in life, it can be surprisingly effective in solving certain computational problems.
Okay, so when are greedy algorithms a good choice?
They're particularly useful when finding the perfect solution is too complex or time-consuming. Sometimes a good enough solution is all you need.
So it's like taking a shortcut that might not be the most scenic route, but it gets you to your destination quickly.
Exactly. There are many examples of greedy algorithms in action. For example, one way to solve the classic knapsack problem, figuring out the most valuable items to fit in a knapsack, is to use a greedy approach.
Okay, I'm starting to see how these greedy algorithms can be both clever and a little bit sneaky.
They are. And they're used in a surprising number of applications, from scheduling tasks to finding the best route in a network.
This is all so fascinating. I'm really enjoying exploring all these algorithms. What else do we have in store?
Let's shift gears and explore dynamic programming. It's a bit more complex, but incredibly powerful. It's all about breaking down a problem into smaller subproblems and storing their solutions to avoid redundant calculations.
Dynamic programming. That sounds like a very methodical approach.
It is. Imagine you're trying to climb a staircase. Instead of taking one giant leap, you take one step at a time, and each step builds upon the previous one. That's kind of how dynamic programming works.
Okay, I can visualize that, but how does this apply to algorithms?
Let's go back to the knapsack problem. A dynamic programming approach would create a table that stores the best possible value for every possible weight of the knapsack. It would systematically fill in this table, building upon the solutions for smaller subproblems until it reaches the final solution for the full knapsack capacity.
So it's like building a tower, brick by brick, making sure each level is solid before adding the next one.
Precisely. And this approach ensures that dynamic programming finds the absolute best solution, unlike greedy algorithms, which can miss the optimal outcome.
Okay, that makes sense. So dynamic programming is like a master planner taking a systematic approach to solve problems.
Exactly. And while it might require more computational effort than greedy algorithms, it guarantees finding the best possible solution.
That's amazing. I'm starting to see how dynamic programming can tackle really complex problems.
And it's used in a lot of applications, from optimizing routes and navigation systems to finding the best alignment for DNA sequences.
Wow. So dynamic programming is helping us unlock the secrets of life itself.
In a way, yes. It's helping us solve some of the most challenging problems in science and technology.
Okay, I'm definitely a fan of dynamic programming now. What other algorithmic wonders await us?
Let's explore the world of K-nearest neighbors, KNN for short. It's a surprisingly simple yet effective algorithm for classification and prediction.
K-nearest neighbors. That sounds intriguing. What exactly does it do?
Imagine you're trying to figure out if a fruit is an orange or a grapefruit based on its size and color. KNN looks at the K closest data points, or neighbors, to the new fruit, and uses their classifications to predict the new fruit's category.
Oh, so it's like asking the fruit's closest friends, hey, what kind of fruit are you? And then going with the majority vote.
Exactly. It's based on the idea that similar things tend to be grouped together.
Okay, that makes sense. So KNN is like a social butterfly, using its network of friends to figure out where it belongs.
You could say that.
Mm.
And this simple idea can be applied to a wide range of problems, from recommending movies on Netflix to classifying emails as spam or not spam.
So it's like a versatile chameleon, adapting to different scenarios based on the data it's given.
Precisely. And what's really neat is that KNN can also be used for regression, which means predicting a numerical value instead of a category.
Okay, so it's not just about classifying things, it can also make predictions about numbers.
Exactly. For example, you could use KNN to predict the price of a house based on its features like size, location, and number of bedrooms. It would look at the prices of similar houses in the neighborhood and use that information to make a prediction.
Wow, that's really impressive. KNN sounds like a real powerhouse algorithm capable of tackling all sorts of challenges.
It is, and it's just one example of the many fascinating algorithms that shape our digital world.
This deep dive has been incredible. I'm already starting to see algorithms in a whole new light.
That's the beauty of exploring this world. Once you start understanding how algorithms work, you start to see their impact everywhere.
I can't wait to see what other algorithmic adventures await us. Welcome back to our algorithm adventure. We're still exploring this amazing world with Grokking algorithms as our guide.
It's like we have a backstage pass to how the digital world works. See all these instructions that solve problems.
Exactly. Last time we went over a bunch of stuff like binary search and k-nearest neighbors.
Right, and there's so much more.
Well, let's dive back in. What else do we have?
Let's talk about sorting. We already talked about quicksort and merge sort a bit, but there's another one called selection sort.
Selection sort. Okay, how does this one work?
Imagine you're organizing a bookshelf. You want to put all the books in order alphabetically. Selection sort goes to the shelf, finds the book that comes first alphabetically, and puts it at the beginning. Then just repeats that process, finding the next book in order, and so on.
So it's like it's picking out the smallest element and putting it where it belongs?
Exactly. It's pretty intuitive and easy to understand.
Yeah.
It's not the most efficient sorting algorithm, though. Yeah. Especially when you have a lot of stuff to sort.
I can see that. If you have a ton of books, it would take forever to keep finding the smallest one.
Right. Selection sort has a time complexity of big O of n squared, meaning the time it takes increases a lot as the number of items grows.
So it's not as speedy as quicksort or merge sort, but it's still useful.
Absolutely. For smaller data sets, when you need something simple, selection sort is a good choice.
Okay, that makes sense. So we've gone over a few sorting algorithms now. What other problems can algorithms help us solve?
Let's get into some number theory with Euclid's algorithm. It's been used for a long time to find something called the greatest common divisor, the GCD of two numbers.
Euclid's algorithm? That sounds pretty old school. What's the greatest common divisor?
It's the biggest number that divides evenly into both of the numbers. Like the GCD of 12 and 8 is 4, because 4 is the largest number that divides into both 12 and 8 with no remainder.
Okay, I see. So Euclid's algorithm helps us find that GCD quickly.
Yes, pretty elegant. Basically, it repeatedly subtracts the smaller number from the larger number until you get 0. The last non-zero result is the GCD.
That sounds simple enough. Can we go through an example?
Sure. Let's say we want to find the GCD of 24 and 18.
Okay.
We start by subtracting the smaller number, 18, from 24. That gives us 6. Now we just repeat with 18 and 6.
Got it. So we just keep going.
Yep. Subtract 6 from 18 gives us 12. So now we have 12 and 6. Again, subtract 6 from 12, we get 6. Then 6 from 6 gives us 0. So
the GCD is 6.
You got it. Euclid's algorithm breaks the problem down into simpler steps to get the solution.
I love how this algorithm is old but still used today.
It really shows how powerful a good algorithm can be.
All right, I'm ready for another one. What's next?
Let's go back to dynamic programming. We'll look at how it can be used to find the longest common substring between two words.
Longest common substring, what's that?
Imagine the words fantastic and fanfare. The longest common substring is fan. It's the longest string of letters they both have.
I see, like finding the biggest overlap between two words.
Exactly. Dynamic programming has a clever way of solving this. It makes a grid where each cell represents the length of the longest common substring between parts of the two words.
Okay, I'm picturing a grid. How do we fill it in?
Well, the first row and column are all zeros. Because you're comparing nothing to something, the length is always 0.
Right, that makes sense. Then what?
You go through each cell and compare the letters at the corresponding positions in the words. If they match, you add 1 to the value from the cell diagonally above and to the left. If they don't match, you just take the biggest value from the cell above or to the left.
So you're kind of building a chain of matches?
Yeah, exactly. And then the largest value in the entire grid is the length of the longest common substring.
That's pretty neat. Dynamic programming is so cool, solving complex problems by breaking them into smaller pieces.
It is. It's used for a lot of things. Like in bioinformatics, it's used to compare DNA sequences, which can help us understand evolution.
Wow. So dynamic programming is helping us learn about life itself.
In a way, yeah. It's helping us solve some tough problems in science and tech.
Okay, I'm sold on dynamic programming. What else is there?
Let's go back to k-nearest neighbors. Remember we talked about how it can be used for regression, predicting a number instead of a category?
Oh, yeah. I'm curious how that works.
Imagine you're trying to predict how much a house will sell for, based on stuff like the size, location, and number of bedrooms. KNN for regression finds the K closest houses and takes the average of their prices to predict the price of the new house.
So it's like asking your neighbors, how much did your house cost? And then using that to guess the price of your house.
Exactly. Similar houses will usually have similar prices.
So it's like a real estate crowdsourcing algorithm.
You could say that. And just like before, the number of neighbors you choose is important to how accurate the prediction is.
If you choose too few, it might be too specific, and too many might be too general.
Exactly. It's all about finding the right balance.
Okay, that makes sense. KNN really is versatile.
It is. It's used for all sorts of things, from predicting stock prices to forecasting the weather.
This is great. I'm really starting to get how powerful algorithms are. What else do we have time for on this deep dive?
Let's talk about spam filtering. Algorithms help us with this every day.
Spam filtering. Oh, yeah. I definitely appreciate those algorithms.
It's a never-ending battle, but we have some clever algorithms to help us. One way to do it is to use a probabilistic algorithm called the naive Bayes classifier.
Naive Bayes classifier. How does that work?
It uses Bayes' theorem. Basically, it figures out the probability of something based on the probability of things that cause it. So for spam, the naive Bayes classifier learns from a bunch of emails that are labeled as spam or not spam. Then it uses that to figure out the likelihood that a new email is spam.
Oh, so it's like a detective gathering evidence.
Yeah. It looks at the words in the email and figures out how often each word shows up in spam versus not spam. Then it uses that to give the email a spam score.
So if an email has a lot of words that are common in spam, it's more likely to get flagged.
Exactly. And even though it's called naive, it works really well.
Why is it called naive, though?
Because it makes a simplifying assumption. It assumes that the words in an email are independent of each other, which isn't always true, but it still works great.
Okay, well, I'm glad we have that algorithm working for us. What other problems can algorithms help solve?
Let's talk about image recognition. This is a field that's been growing a lot thanks to algorithms.
Image recognition. Yeah, that's fascinating. How do computers even see images?
One important technique is called optical character recognition, or OCR. It lets computers read text from images.
Oh, wow. So like if I scan a document, OCR can turn it into text I can edit.
Exactly. It's a complex process involving a lot of analysis of the shapes in the image to recognize the letters.
That sounds really hard. How do algorithms do that?
It uses a few techniques, like image preprocessing and character segmentation. Machine learning algorithms, like KNN, actually play a big role in recognizing the characters.
So it's like a team effort with
Yeah.
different algorithms all working together.
Yeah. And OCR has tons of uses. It's used for digitizing books, recognizing license plates, and even helping visually impaired people read text with assistive devices.
That's incredible. Algorithms really are bridging the gap between the physical and digital worlds.
They really are changing how we interact with information and tech.
Okay, let's keep going on our algorithm exploration. What's next?
Let's talk about parallel algorithms. These algorithms are designed to use multiple processors to speed up computation.
Parallel algorithms. Sounds powerful.
They are. Imagine you're trying to sort a huge list of numbers. Instead of doing it on one processor, a parallel algorithm could divide the list up, sort each part separately, and then combine the results.
Oh, so it's like having a team of workers tackling the problem all at once.
Exactly. This can save a lot of time.
That makes sense. Are parallel algorithms hard to design, though?
They can be trickier than normal algorithms. You have
Yeah.
to think about things like how the processors talk to each other and make sure they're all working together efficiently.
So it's like conducting an orchestra.
That's a good one. And parallel algorithms are super important for handling massive data sets, especially in things like scientific computing and machine learning.
Okay, I'm seeing how important they are, especially as we get more and more data.
Right. And with cloud computing, they're becoming easier to use too.
It's like having a bigger and better orchestra to play with. This is all so cool. What else is there?
Let's dive into distributed algorithms, a type of parallel algorithm that's designed to run on a network of computers.
Distributed algorithms. How are those different from parallel algorithms?
Well, parallel algorithms can run on one computer with multiple processors. But distributed algorithms are made to run on a whole bunch of computers. This lets them work with massive data sets.
Oh, so it's like having a whole team of experts working together.
Exactly. A famous distributed algorithm is called MapReduce. It's great for processing huge amounts of data.
MapReduce. I think I've heard of that.
It's used in a lot of big data systems, like by Google and Facebook. It uses two main operations, map and reduce.
Okay, what do those do?
Map takes a data set and applies a function to each item, often at the same time. Then reduce combines the results from all the maps.
So it's like dividing a task into smaller chunks and then putting the answers together.
Exactly. This is really useful for analyzing huge data sets. Like imagine you want to count how many times each word appears in millions of documents.
Oh, yeah, that would be a lot.
With MapReduce, you could map each document to a list of word counts and then reduce all those lists to get the total count for each word across all the documents.
Oh, wow, that's clever.
And because it can be done on lots of computers at the same time, MapReduce can handle massive amounts of data.
That's awesome. It's like a data crunching machine.
Right. And they're becoming more and more important as we keep getting more and more data.
Okay, I'm ready for our next adventure. What else is there?
Let's talk about a common problem with big data sets. Figuring out if something is in a set.
Okay, yeah, that sounds like a basic problem. But I bet it gets hard when the set is really big.
Exactly. Hash tables are good for this because they're fast. But if the set is really, really big, they might not have enough memory.
So we need a different approach for those cases.
Right. That's where Bloom filters come in. They're special data structures that are good at representing sets and checking for membership, even with limited memory.
What are Bloom filters?
A Bloom filter uses multiple hash functions to represent a set in a small space. To see if something's in the set, you apply those hash functions and check certain bits in the Bloom filter.
So it's like using multiple clues to solve a mystery?
Yeah, kind of. But there's a chance of false positives. The filter might say something's in the set when it's actually not.
Oh, so it's like a detective making a mistake.
Yeah. But the cool thing about Bloom filters is that they're really efficient with memory. They can represent huge sets using a small amount of space.
Okay, so it's a trade-off.
Yeah, exactly. And for a lot of things, like web caching, it's okay to have a few false positives.
So it's a quick and easy way to check for membership. Nice.
Exactly. Bloom filters are a really elegant solution to a tough problem.
I'm starting to get into these data structures. What else do we have?
Well, let's talk about hyperlog. It's another really cool data structure. It's good for estimating how many unique things are in a set.
Hyperlog, what a name. Why would we need to just estimate that? Why not count them all?
Counting unique things can take a lot of memory, especially if the data set is huge. Like imagine trying to count how many different people visit a website with millions of users.
Yeah, that would be tough. So how does hyperlog make it easier?
It uses a clever trick. It looks at patterns in the binary representation of hash values. Using that, it can estimate the number of unique things with pretty good accuracy using much less memory.
So it's like a super efficient pollster using a small sample to predict an election.
Yeah, that's a good analogy. This makes it good for things like counting how many unique users there are or analyzing network traffic.
It's amazing how algorithms can make sense of so much data without using too much memory.
Definitely. And as we get more and more data, these algorithms are going to become even more important.
Okay, what's next on our algorithm journey?
Let's get into the world of cryptography. We'll talk about something called hashing.
Hashing. That sounds familiar. Didn't we talk about that with hash tables?
Yeah, hash tables use hash functions to organize data. But in cryptography, we use secure hash algorithms to make sure data is safe.
Okay, so how do they work?
They take something like a password or a document
Sure.
and create a unique hash value. Think of it like a digital fingerprint.
Oh, so if you change even one thing in the message, the hash is totally different.
Right. That makes it almost impossible to mess with the message without getting caught. A popular one is called SHA-256.
SHA-256, I've probably seen that before.
Yeah, like when you create an account online, the website probably uses SHA-256 to store your password.
Oh, wow. So they don't actually store the password, just the hash.
Right. So even if someone hacks the website, they can't steal your password. It's too hard to reverse the process.
That makes me feel better. So hashing is like a shield for our information.
Exactly. It's super important for security online, like for banking and messaging apps.
Okay, I'm convinced. What else do we have in the world of cryptography?
How about the Diffie-Hellman key exchange? This one's pretty revolutionary.
Diffie-Hellman key exchange, what's so special about it?
It lets two people create a shared secret key, even if they're talking on an insecure channel.
Wait, how is that possible? If
Yeah.
anyone can listen in, won't they steal the key?
That's the cool part. It uses some clever math to make sure that even if someone is listening, they can't figure out the key.
Okay, I need to hear more about this.
Imagine two people, Alice and Bob, want to talk secretly. They each have a public key and a private key. They share their public keys but keep the private ones secret.
Okay, so some information is public, some is private.
Right. And then using some math with their public and private keys, they can create a shared secret key without ever actually sending the key directly.
Whoa, that's crazy. So even if someone hears them talking about the public keys, they can't figure out the shared secret key.
Exactly. It's like having two secret ingredients for a potion. Each person has one ingredient, but you need both to make the potion.
I love that analogy. So Diffie-Hellman is like a secret handshake, but with math.
Uh-huh. Exactly. It's used all over the place to keep communication secure.
Okay, that is super clever. What other amazing algorithms do we have time for today?
Let's switch gears and talk about optimization problems. These are all about finding the best solution out of a bunch of possibilities.
Optimization problems. Okay. What kind of problems are those?
A classic example is the traveling salesperson problem. It's a famous puzzle.
Traveling salesperson problem. I've heard of that, but I don't really know what it is.
Imagine you have to visit a bunch of cities and then go back to where you started. The goal is to find the shortest route that visits each city only once.
Oh, that sounds tough. Especially if you have a lot of cities.
Exactly. It's a really hard problem to solve perfectly,
No.
especially when there are a lot of cities.
So there's no algorithm that can solve it perfectly.
Not for a lot of cities. There are algorithms that work for small cases, but for lots of cities, it would take way too long.
So it's like trying to find a needle in a haystack, but the haystack keeps getting bigger.
Uh-huh, yeah. But even though we can't find the absolute best solution, we can find pretty good ones that are fast enough to use.
So it's like finding a good parking spot, even if it's not the absolute closest one.
Exactly. And these algorithms are used a lot in things like planning routes and designing networks.
Okay, that makes sense. So even with hard problems, we can still find solutions that work well enough.
Exactly. And the traveling salesperson problem shows up in a lot of places, like in logistics and even DNA sequencing.
Wow, that's really cool. This puzzle is more important than I thought.
It is. It shows how a simple problem in math can have connections to all sorts of things in the real world.
Okay, I'm seeing how connected all this is. What else do we have in our deep dive?
Let's talk about locality-sensitive hashing. It's good at finding similar items in massive data sets.
Locality-sensitive hashing. What is that?
Imagine you have a ton of pictures, and you want to find all the ones that are similar to a specific picture. Locality-sensitive hashing can do that quickly.
Oh, okay, I'm picturing a huge library of pictures. How does it work?
It uses special hash functions that are designed so similar items end up with similar hash values. So pictures that look alike are more likely to have similar hash values.
So it's like sorting them by their visual fingerprints.
Exactly. And that makes it way faster to find similar images. Instead of comparing every picture to every other picture, we can just compare their hash values, which is much faster.
So it's like taking a shortcut.
Yep. And a popular algorithm for this is called SimHash.
SimHash. That sounds nice and simple.
It is. It's used for things like finding duplicate web pages and even detecting plagiarism.
Wow, that's really useful. So it's like a digital detective.
Uh-huh. You could say that. It's another great example of how algorithms help us deal with tons of data.
I'm really liking SimHash. What else is there?
How about randomized algorithms? These algorithms use randomness to solve problems that are really hard to solve otherwise.
Randomized algorithms. That sounds kind of chaotic. Why would we want to add randomness to algorithms?
It might seem strange, but sometimes randomness can actually help. Think about quicksort. Remember how we talked about choosing a pivot element?
Yeah, and how the choice of pivot can make the algorithm faster or slower.
Right. If we choose the pivot randomly, we can avoid the worst-case scenario and make the algorithm faster on average.
So it's like shuffling a deck of cards to make sure they're all mixed up.
Yeah, good analogy. That's just one example. Randomized algorithms are used in lots of areas. from cryptography to machine learning.
Okay, I'm starting to see how randomness can be useful.
It's a really cool area of study. Always new discoveries being made.
Okay, what's next?
Well, we've talked about them a little bit already, but let's discuss approximation algorithms in more detail.
Approximation algorithms.
Yeah. Remember the traveling salesperson problem? We talked about how it's impossible to find the absolute best solution when you have lots of cities.
Yes. So approximation algorithms help us find good enough solutions.
Exactly. They might not find the very best one, but they can find one that's close enough and way faster.
Like finding a decent parking spot, even if it's not the very closest one.
Haha, perfect analogy. These are used all the time, like for scheduling tasks and designing networks.
They sound really practical.
They are. They're essential for complicated problems where finding the perfect solution just takes too long.
All right, what's next on our adventure?
How about online algorithms? These algorithms deal with data that comes in one piece at a time instead of all at once.
Online algorithms. Okay. When would we need those?
Imagine you're running a server that's always getting requests. You have to decide which requests to handle right away and which ones to put in a queue for later.
Oh yeah, that makes sense. You don't know what's coming next.
Exactly. Online algorithms are made to make decisions in the moment without knowing what's going to happen in the future.
So it's like they're improvising.
Yeah, good one. They're used in a lot of things like caching and routing.
Okay, so they're good at handling data that's always changing.
Right. Online algorithms show how adaptable they can be.
Okay, what else is there? This is all so interesting.
How about streaming algorithms? These are for handling huge data sets that are too big to even fit in your computer's memory.
Streaming algorithms? Wow, that sounds hard. How do they even work?
They look at the data one piece at a time. And they can only go through the data once, so they have to figure things out and make decisions really quickly.
Whoa, so it's like drinking from a fire hose.
Yeah, streaming algorithms are really important for analyzing real-time data, like stuff from social media or sensors.
That makes sense. You can't just stop the data and analyze it.
Exactly. Streaming algorithms are made to be really fast and efficient with memory.
So they're like super efficient data processing machines.
Exactly. And as we get more real-time data, they're going to be even more important.
Wow, this is amazing stuff. What else do we have time for?
Let's talk about machine learning algorithms. These algorithms let computers learn from data without being specifically programmed.
Machine learning. That's a popular topic these days. I hear it's behind self-driving cars and personalized recommendations.
You're right. It's changing a lot of industries. It's based on the idea that computers can find patterns in data and learn from it.
Okay, so how do they actually learn?
There are a lot of different kinds, but there are two main types: supervised and unsupervised learning.
Okay, what's the difference?
In supervised learning, you give the algorithm some data, and you tell it what the answer should be for each piece of data. Like you might give it a bunch of emails and tell which ones are spam. Then it learns from that to predict if new emails are spam.
So it's like a student learning from a teacher.
Yeah.
Welcome back to our algorithm adventure. It feels like we've explored so much already, from sorting to cryptography, and now we're talking about machine learning.
Right. Algorithms are doing more than just solving problems now. It's like they're learning.
Exactly. Last time we were talking about supervised learning, where algorithms learn from data that's labeled. What about unsupervised learning? How do algorithms learn without those labels?
Think of it like this. You have a basket of different fruits, but there aren't any labels. You might group them together based on how they look, like their color or size, without knowing their names. That's kind of like unsupervised learning.
So it's like finding patterns in data without being told what to look for.
Exactly. One common example is clustering, where the algorithm puts similar things together. Like a music streaming service could use clustering to group songs that sound alike without needing to know the genre.
Okay, so it's like an explorer, discovering hidden connections in the data.
Exactly. And it's used in all sorts of things, like understanding customer groups, finding unusual data, and even helping scientists make sense of complex data.
This is so cool. Machine learning is really pushing the limits of what algorithms can do.
It really is. And with more data and computing power available, machine learning is changing so many industries.
Well, with Grokking algorithms, we've been through so many different algorithms, from the basics to some really advanced stuff.
It has been a great journey, and remember, this is just the start. There's always something new to discover with algorithms.
This has made me want to learn even more. Any advice for people who want to get into algorithms?
Definitely. Don't give up. Stay curious. Keep exploring. Algorithms are like puzzles to solve, and the more you learn, the more amazing they become.
Great advice.
Yeah.
And to everyone listening, thanks for joining us on this deep dive into the world of algorithms. We'll see you next time.